Welcome to another edition of Programming Lux, the debugger. Lux is a new debugger, a brand new, never before seen, I'm gonna totally hype it up, revolutionary debugger. It's gonna change the way debuggers work. Everything about it is being completely rethought from scratch. And every Tuesday, I have a stream where I program part of the debugger as I'm building it. The debugger, is still in alpha right now. And you can join the alpha and try out the debugger for yourself and offer the development team direct feedback. Just go to luxdebugger.com and there's a sign up at the bottom of the page. Today, we will be building native visualizers using Clang emulation on today's debugger stream. And I take any questions during the entire stream. I'm happy to explain anything about how the debugger works. So let me explain what native visualizers are. If I go to Visual Studio, okay, native visualizers are Visual Studio. I didn't check whether there's audio on the stream here. Good. Native visualizers are a Visual Studio thing that they developed originally. And what they do is, you have here a stud vector. A stud vector on the inside is actually kind of weird. There is, it's just this compressed pair thing. Without knowing anything about why Microsoft built it this way, you would not be blamed for being confused about why a stud vector comprises a compressed pair. And so if you are naively trying to discover what is inside the vector, you would look in this pair and you would see a bunch of junk you don't understand. I actually want my data. Where's my data? What is this pair thing? Okay, so what Visual Studio built is called a native visualizer, which is this XML file, which every instance of Visual Studio, every installation of Visual Studio has this XML file. And you can see here actually let's look, stud vector. It has a description of what is in the stud vector and how to get meaningful information out of it. Okay, so we have size, capacity. In order to calculate the size, you actually have to calculate this expression. Why this expression? The implementer knows. We don't have to. We just have to faithfully calculate these expressions in order to calculate the size and capacity. And you also are able to display a list of all items in the debugger by telling the native visualizer the size of the debugger, which you calculated up here, and the first item in the list. And if you do that, then Visual Studio will print. We have nothing here because we have nothing in the, but let's add something. And there it is. Okay, so Visual Studio has opened, has interpreted through the native visualizer what should actually be in this vector. I've pushed two items onto the vector. So this is what we're doing today. If you look in the raw view, you're not able to actually see anything but the first item right here because this is how it is stored internally. And you need the native visualizer to do that. So in order to load a native visualizer, you have to do 3 steps. Yes, 3 steps. All of which I've taken the first steps of so far, but I haven't completed, and we're going to complete some of those steps here on the stream today so we can see how it works. The first step is to load this XML. And I have done that. NatViz. Okay, I have a very simple XML loader which looks at the reflection that I have in my, I have a reflection system in my code. It matches the data in the NatViz file with the reflection data in my program. And so it knows to map this type object. This is what this code right here is doing. It knows to map this type object to this type object. Okay. Now this type object has subtypes, not subtypes, but contained types: intrinsic, display string, expand. And then here they are: intrinsic, display string, expand. And it knows to map these to these types. And so all I have to do is call this function loadXML, and the xml.cpp file looks through this code, grabs all of the XML, and creates these objects right here. And I just get a big in-memory tree that represents the XML. And so I've loaded my XML into memory. Again, I answer all questions about all of this. If you have questions, feel free to ask anytime. I'm happy to explain in more depth any of the things that you're seeing here. So once we have an in-memory representation, then we load it into this library. A NatViz file is just the auto visualizer is like the top level of the XML. Okay, so we have a NatViz file. We load it into this library, and then we have to find visualizers for a type name. So we say, hey, I have a stud vector. I want all of the visualizers in this file that match name stud vector. We return that. Okay, we have that in this list. And now let's see, find visualizers. Okay, so we have this list of visualizers that match the name, and we have to go through in priority order, because you can see each one has a let me boop. Where'd it go? Can't type. Each one has a priority. This one's medium low, the default is medium. So we have to look in priority order and evaluate them. And the first one that can properly evaluate all of the expressions contained therein is a valid visualizer for this data structure. The reason that they do that is so that Visual Studio 2015 can still read old versions of the standard template library. Standard template library used to have stud vector laid out a different way, a more straightforward way before they added this myPair. It was an optimization. And so if you are debugging with Visual Studio 2015 or later, a program that was compiled with an earlier 2013 or earlier version of Visual Studio, you can still read it because the 2013 format is here. In that case, this evaluation will fail. It won't find the myPair. It will fall back to the 2013 version, in which case it will see the my end and my last and my first version without myPair, and it will use this. So that's why you have the priority order. So the thing you have to do is to evaluate each visualizer is go through each of these, see whether they are valid C++, essentially compile them. You essentially have to compile this and to tell whether it's a valid little C++ program here, as if it were in the contents of a method inside the scope of this class. Now, I talked a little bit about this on the last stream that didn't make it up to YouTube. How do I go about doing that? I can definitely write my own C++ evaluator and compiler, and that would be a lot of work. So what I've done instead is, because I'm going to need to use Clang in the future, Clang, also known as Clang, is an open source C++ compiler that anyone can integrate into their applications and use as a library. And that's what I've done. I have CPP parser, and on stream last time, in the stream that didn't make it up to YouTube, I struggled, to be honest with you, to figure out how to integrate Clang. I eventually did figure it out. And here I have the Clang header files included. I have some helper classes, and then the important code is, let's look at it right here. Let's look at a parse expression in scope. So this expression right here is sent directly to Clang. It's sent directly into this file, parse expression in scope. Okay, we crunch a bunch of data to make sure that we're prepared. This is the dependent classes function is the important function. In fact, I'm going to set a breakpoint here so that we can see exactly how it works, because it's kind of interesting. Dependent classes. So let's do that. What I have to do, Clang doesn't support the idea of building, of parsing just a sub-expression of C++. It can only parse on the order of a complete file. And so what I have to do is build a fake complete vector class out of this expression. This expression is designed to be run inside a fake a vector class. So I construct a fake one around this class. So here I pass in, hey, give me all of the classes that I depend on in order to create a stud vector right here. Okay? That's what this function does. It will return all of the dependent code that I need in order to write a fake vector class and a fake function inside of it in order to put that expression in order to compile it. So you see what it does is it goes through the members of this vector, of an actual vector. It has pulled this out of the DIA-SDK, which I described in the last stream, that I use to query the types present in an executable. So I'm not compiling the vector class. I'm taking the already compiled information out of the program that I'm debugging. Okay, and that contains information. Here it is about all of its stuff and you can see here's the myval2. Wait, hold on. User defined type. Wait, type stud vector is a user defined type with one member, myval2, which is a vector val class. That's interesting. I would have expected it to have the my pair first. Oh wait, I know why that is. No, I don't know why that is. Really? I would have expected it to have the my pair as the member. Interesting. I'm missing something, but it's not that important. And so oh wait, here it is right here. Member compressed pair. Oh, of course. This is getting the type of the, I'm just looking at the wrong thing. Here it is. I should be looking at this one. Yeah, I was just looking at the wrong thing. So the vector contains this my pair thing. Here it is. Okay, which is a compressed pair. I got all of this information out of the program that I'm debugging. And so I'm going to spit out a fake compressed pair. And a compressed pair has what? It has a member that is a fake, that is a vector val. And so I'm going to spit out a fake vector val. And what is a vector val? A vector val has, these three members in it: my first, my last, my end. Okay, so none of these are user-defined types. So the result is we make a fake vector val which contains a bunch of fields. Hold on, here we go. Okay, a fake vector val that has all these fake fields. And then that is placed next to a fake compressed pair, which has the vector val. And then that is returned back here and assembled into a fake C++ file, which I will show you momentarily. Okay, this is the code that I'm going to compile. All right, so we have the fake vector val class, fake compressed pair, fake vector, containing a fake function f containing the expression that I want to evaluate. Notice we don't actually do anything with this expression because we're not fully compiling using Clang. We're just going to do the parsing stage and get an abstract syntax tree out of Clang, also called an AST. Okay. Once we have the AST, then we're going to take it over from there. Clang is only going to do the front end work. If you're familiar with compiler construction, this is the front end. We're not actually going to emit any code. We're just interested in the AST, and we're going to evaluate the AST directly. Okay, so this build AST from code function does some stuff, but eventually calls directly into Clang in order to start their compiler front end and returns to me an AST, which is an in-memory representation of the program that I compiled, which is called input.cc. It's just like the fake name for the fake program that I compiled. Here's all the data for that stuff. You can't just read this data. That's not how Clang works. You can't just understand it by looking, or at least I haven't figured out how to understand it by looking at all this stuff. You have to call some more functions on it. It won't just tell you what's in there. For example, you can get the translation unit, which is a translation unit is just another name for a C++ file, right? So we fed it a fake C++ file. So this variable now represents the root of that tree, something that encapsulates the entire C++ file. We're going to search it using this find named method visitor that I wrote for a function named stud vector : f, which is the fake function that we made that has the expression we want to evaluate in it. So we find that method declaration. The method declaration item is a node in the tree representing the, actually, hey, I wonder whether I can show you, okay, I closed it here, but I wonder whether I can show you in the logs. There was a time when I printed out a bunch of ASTs to the logs. When was I working on this? It would have been about here. I found some. Okay. This is a log where, for testing purposes, I have printed out the AST, the abstract syntax tree. And you can see this is a bunch of stuff that Clang automatically puts in every file that it builds. For some reason, you see it's just a bunch of default stuff. It wants to define 128-bit integers, constant strings. I don't know why it feels like a VA list, stuff that it feels should be part of every C++ program, even though I'm not going to use it, but it's not hurting me any. So, and you can see this looks an awful lot like the thing that I just showed you. Namespace declaration stud containing a vector val containing these three variables, another stud containing a compressed pair containing one more variable. You can see it's just a big tree that is the program that I am compiling. And then I got lucky, and this is one that actually doesn't have any errors because I parsed a lot of them that had weird errors and stuff. But good, we're looking at a good one. And then here's my fake function f with a compound statement in it that has a binary operator, the subtraction operator, that subtracts to sub-expressions and so on. And so if I can walk this tree, then I can evaluate the expression. So this is what we've found here. This CXX method declaration we found is this guy, okay? And we know that inside it, there's going to be a compound statement And so we're going to get that compound statement. And it will have a substatement, in other words, an expression. It should have exactly 1. If it does not, that means that there was an error. Otherwise, it should have exactly 1 substatement because we only put 1 statement in this function. So we assert for 1 substatement. We get that substatement, and then we return that expression as the result of the parse. Okay? So my evaluate CPP file calls parse expression in scope, okay? And then evaluate. And let's look at what evaluate does. Evaluate just wants to, it takes the expression, the AST of just the expression node, so we're starting at this node right here, and then it tries to figure out what it is and evaluates it. So I already have an implementation for binary operator because that's what I needed. Okay, and so it just recursively evaluates the left and the right side of the binary operator. See, this is going to be the result of the left side, the left value. Let's see. It has the value, which it puts in a little buffer here. It looks like a pointer of some kind. And then the type of that, which I believe should be a pointer. Yeah, it's a pointer. So it evaluates the left side of the expression. Let's walk in and see what it does to evaluate the right side of the expression. So it has already, because I stepped over this code, it has already evaluated this side of the expression. So now we're looking in here, and we should see an implicit cast expression. So not a binary operator, not a unary operator, not a member expression, not a this expression, but a cast expression. Implicit cast expression is, of course, a subclass of cast expression. All right, so it just calls evaluate again. So this is all it's doing. It's walking this abstract syntax tree. Every time it does, it calls evaluate again until it gets to the very bottom, which is a CXX this expression. You can see the CXX this expression is at the very bottom of the tree. It's the leaf node of the tree. And this just, I actually pass this pointer into the function. It's one of the parameters of the evaluate. There it is, okay? And so I just pass it on in there. It loads it into the value that it returns. And then it gets a member value. You get it from here, folks. If you have specific questions, let me know. I'm happy to go into more of what these nodes do, but it just evaluates all of the nodes. If you're wondering, like, how does it evaluate node X? Well, member expression is just pointer math. It just does pointer math, right? If I have an object and I want to get a member, then you're just doing math on the pointers of the values to get that value. So, and then it does the actual subtraction at some point, and there it is. This is the actual subtraction right here. So that's how the evaluator works. All right, I've explained everything. It's time to figure out what am I actually going to do with this data. So let's look at where the debugger is right now. If I load up Lux, put a breakpoint right there. Get rid of the breakpoint that I set before. Okay. The place where I am right now is that my native visualizer, which I've loaded from Visual Studio. I'm basically just stealing Visual Studio's native visualizers. If you have any copy of Visual Studio installed, any version, it will go and find the latest version and load those native visualizers, and right, and all this should work. And it will, I've got it showing the size right here. It had to evaluate this expression, this size expression, so all that worked. That's, in fact, we were just looking at this code that evaluates that size expression. Close that log. Okay. It evaluated this, to get this capacity 1, it evaluated this capacity expression. Okay. Which is similar, except these two right here are different. So let's see that at work as I press F10 to get through this thing. Okay. Size and capacity are both 1. They're both 2. They're both 3. They're both 4. And now it should switch over from the... There's like an optimization in stud vector where if the vector is small enough, it just stores it inside the vector. But once it gets too large as an optimization, it can't store it in the locally in the vector anymore. And so now it allocates some memory outside. And so you can see it allocated enough for 6 items, even though there are only 5. And then I add one more. Now there are 6 and the capacity is 6. When I add another one, the capacity goes up to 9. Even though the size is 7. So you can see the allocator at work. So now the only thing that we have to do remaining in order to get a fully functioning stud vector is to interpret these array items. So array items is a special field that has a size and a value pointer. And if you give it the size and the value pointer, the intention is that the native visualizer should know what that means and should start an array of this size at this pointer, showing in memory each item in the array and interpreting it as the type, whatever the type is of the vector. Actually, that's a good question. How does it know what the type is? It never explicitly says the type, does it? Yeah, it must implicitly assume. There must be something about the logic of native visualizers. I have the documentation right here. This just occurred to me as I was looking at it. Array items. Let's see here. Okay. Array items. Use the array items node to have the Visual Studio debugger. Okay. It's a good example. So the array item must have a size and a value pointer. Default value. It doesn't say anything about the type. You can also specify multi-dimensional arrays. That's cool. Direction, size. Yep. Okay. Well, then I will assume that, yeah, this documentation is a little bit spotty. In other places, it in a vector bool, it explicitly casts to a bool. Oh, of course, I know. The type has to be the type of this expression. Yeah. Of course, it will. So it will use whatever the type of this expression is. It will just return that. Okay. Yep, that's obvious. So that's why it casts it right here. It casts it to a bool. It says, hey, my index list items. Oh, that's interesting. That's different from array items. Anyway, my items are going to be, because it has, it's like a different feature. It has $i. Anyway, my list items are going to be bools, not whatever the type of this is. I'm going to cast it to a bool. And so it should expect, the native visualizer should expect the type bool instead of whatever it is. Okay, so what we're going to do today, after all this explaining, I've finally gotten to the point. What we're going to do today is make this work. Make it so that it reads this array items XML and then outputs the array items right here. By this point, we've pushed 7 things onto the list, so size 7, and so we should see 7 things right here, and that way we can understand what the stud vector is. Before we do that, I want to talk about a slightly different way of implementing this entire thing that I realized as I was doing this makes native visualizers kind of somewhat obsolete. It takes away a lot, not all of the utility of native visualizers, but a lot of them, okay? So let's say you have a class. This is the assumption that you have to make. Let's say that you have a class that emulates stud vector. which these days, the standard library has been around so long and they generally make good decisions, and it benefits people to, what are you, okay, fine, okay. And it generally is a good idea to emulate them because then you get other benefits in the language, like range-based for loops and stuff, and you get interoperations with other libraries. And so even people who, like here's EASTL, okay? EA, for all of their internal games, they don't use the standard library. They use EASTL, which is EA's version of the standard template library. Okay, so they have their own studvector.h. There it is. Which has all the same, which has this, it has this same, it's like 98% of this is the same. So if I wanted to look for, you know, size, or I guess, wait, is that going to work? Oh yeah, it did work. There you go. We have vector, allocator, size, right? Like it's all the same stuff. All of the game engines generally have containers that look like stud vectors, and there are a lot of private containers that look like stud vector. And the standard template library has 3 different implementations. You have the Microsoft implementation. These are just the major implementations. The Clang implementation and the GNU implementation. But they all look the same. So you actually don't need a native visualizer. What you could do is say, hey, emulate a call, just like I've been emulating this code right here, okay? Emulate a call to stud vector begin. Emulate a call to stud vector end. Emulate the begin returns an iterator, okay? Begin iterator. Emulate a call to that iterator increment. Is there anywhere? Can I click anywhere to view the iterator? Not on this page, apparently. Iterator. 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 Maybe here. Yeah. Every iterator has like a plus plus operator. Hello? +1. So you could like plus here like this, like a +1 to increment the iterator. Okay. If all of these exist, and I already have the capacity to use Clang to parse arbitrary expressions, then I can just write something that uses that implementation, and then, so that gets me automatic, without having to write any XML, visualizers for every standard template library, for every library that looks like the standard template library. Okay. I still have to, I have to do a little bit more work because I have to tear apart stud vector and look at what it looks like underneath. I wonder, can I actually, will this let me open this? No, it's not that smart. Actually, I could do it over here. Let's see. So like if I wanted to open stud string, I would have to, let's see here, cster. Yeah, I would have to parse this code. And so I would have to compile Microsoft's standard template library with Clang, with my Clang emulator, in order to pull this out and know what's in there underneath. So it's a bit strictly more work that I'm doing, but I could do it, and I'm considering doing it at some point in the future, and then that gets me every template library for free. I'm probably going to continue doing the Microsoft standard template library, the Microsoft native visualizer approach, and then when I go to another compiler, instead of duplicating all the native visualizers that Microsoft did for these other compilers, I'm just going to switch over, once I start supporting another compiler, to doing it this universal way. The benefit, if I do this, of remaining to have native visualizers is that it doesn't have to conform to the standard template library format way of doing things. You could write native visualizers for anything. So it's still a feature worth having, which is why I haven't just gone back and started doing it all over again, anything crazy like that. Okay. So, give me 1 second and then we'll start. Okay, so let's do it. Our job, as I've said before, is to get these array items to appear right here in this list. Okay, I've actually forget how much progress I've made on this. So, the first question is, have I loaded it into the, looks like I haven't. So you see that a type has an expand, and expand has an array items. My type has an expand has items but not array items. Item but not array items. Okay, so this is the first thing to do. Array items. Does array items have any properties? I don't think so. Okay. Array items is going to have an object called size. This is almost certainly going to have, let me see, array items. Array items is almost certainly, like, the XML parser supports having an arbitrary number of child elements in the XML file. The fact that Sublime made this a different color worries me. Anyway, the XML parser supports an arbitrary number, but in this case, we're only going to ever have exactly one. But we still have to use the vector, just because that's how the XML loader works. Oops, I keep thumbing over the wrong thing. And then a value pointer. So a size, and then a value pointer. Value pointers. Okay. And then making a member call that is a string called m_inner text is the way you tell the XML loader to put the inner text, in other words, this text or this text, into that element. Okay, so that should do it. Oh, and expand has to have a vector of array items. Array items. Uh-oh. I think I actually have to put an extra S here. Yeah, unfortunate. Unfortunate S. So what's happening here is the XML parser assumes that it's not already pluralized, because none of these other names are pluralized, except whoever wrote this put a plural there. So I would have to, do some like English manipulation and be like, if there's already an S on the end, don't add an S. But I am actually not even gonna worry about that. I'm just gonna have an extra S. Oh man, xml.cpp. Where's the extra S? Stud vector. Oh, here it is. Attribute name. So it's looking for an attribute called... Oh, actually, it doesn't matter what I name this. That's right. Okay, so the way I did it is... It doesn't matter what I named this. The way I did it is I'm looking for an attribute... I'm actually looking for a field of type vector. Yeah, oh, I was even looking at the wrong code. I'm looking for a field that is type of vector of a thing that I'm trying to, like a type of vector, a type array items. And I don't actually care what the variable name is. So I can just call it value pointers. I don't have to put the extra S. Okay, cool. So value pointer. So because this is C++ and we can't have nice things, I'm not actually done. I have to add it to this macro soup reflection table. I would like to get rid of this at some point, by hopefully C++ adds reflection. For some reason, they're making it compile time reflection and not and not runtime reflection. And this is going to be my my bridge between the two until they actually implement reflection. I'm just going to have all this macro soup that is my reflection table. So that's no big deal. I have to find the expand. It just means that if I add something, I have to add it in two places. There's not that much room for mistake here, because the way it ends up is that if you make a mistake, there's usually a pretty obvious error message somewhere that's telling you. So there's just like a little bit more of kind of brainless copy pasting stuff. Yeah, that different color on the size variable really worries me. That is no bueno. Okay. And value pointer. And then we need one more for size. So we're just duplicating. Okay. Now let's compile that and see whether that capital S size has screwed us. If it has, then I'm in big trouble. Oh, no, it looks okay. It compiled. Okay, well. Sublime thinks that this is a language construct somehow, but the compiler seems to disagree. Yeah, like I couldn't name it size of. that would definitely be wrong. Like I took a risk when I did this implementation of the XML loader that nobody ever called one of their elements size of or something like that, right? That would have just killed the whole thing. That would be no bueno. Okay. So that should actually be it. All of the serialization stuff is now done under the scenes. All I have to do at this point is no, not GUI. Oh. I'm looking at the wrong thing here. I want natviz.cpp. Yeah, natviz.cpp. Okay. If I run this now, between the XML loading code and the reflection code, oh my god, it didn't actually run. Hello? Evaluate visualizer? Was never called? I'm confused. Let's try that again. Why was evaluate visualizer never? I have 0 visualizers available. Was there an but there was like a parsing error that I have to work out. Probably. Let's look at the logs. Okay. Parsing. Here we go. Failing to unserialize XML because required attribute mCondition for element array items was not found. Okay, so array items apparently have conditions. So the way I implemented this XML parser is that it is optional to load, like I wasn't loading array items before, even though there was an array item element here. It is optional to load sub-elements, but it is required to load attributes, okay? And I did it this way so that I wouldn't lose track of any attributes that I need. This is definitely not a general purpose XML loader. This is a purpose for what I need for this project right now, XML loader. I'm not trying to write it in the most general. I'm not trying to support elements named size of, you know, like I'm not trying to go crazy here. with general purpose engineering. I'm really just trying to solve the problem that's in front of me. And so I just need to make it so that array items support conditions. Super easy. Okay. I'm actually going to, I used to have a breakpoint at the line of code. Here you go. I'll put it there. Let's try that. Okay. Got another error here. Let's see what's up. Failing to unserialize required M condition for element value pointer isn't present. Okay. So value pointer can also support a condition. So we'll just do the same thing. Value pointer supports a condition. I'm not actually using that condition for stud vector, so I'm not going to implement the condition right now. That I don't want to get distracted. There's so much stuff to do here that, yeah, like it's not even in this file. Like I don't think I need it to support anything in this file, actually. I need it to support... There are a bunch of different NatVis files that Visual Studio provides, and it loads all of them in this directory, even though I only support this one right here for now. Or at least I'm only going to support that in the short term. Eventually I'll have to implement all of NatVis, but I'm only focusing on one thing at a time. This thing is so complicated that if you don't focus on one thing at a time, then you're just never going to finish anything. I thought I pressed F5. You have to take a small chunk of the complexity and bite only that small chunk off at a time, or you will never finish anything. Okay, so now we actually have some visualizers, good, and we will evaluate them, good. All right. So now I can write some code. Oh, I forgot to actually do the thing I was going to look at. Let's try again. Try again. Okay, so my visualizer should automatically get, let's see, expand. And there it is, array items. There's only one. And there's one sizes and one value pointers. We know what's in sizes, the size. And we know what's in value pointers. And then here's the text we loaded. Great, so we got all that XML loading code essentially for free. Our reflection system did it for us. Okay. So we have loaded the XML now. And I need to now go to natviz.cpp. Okay. Into the evaluate visualizer class. So in this code somewhere, I need to write some processing for, say I process items and I process display string. These are the things that I process. So I need to add some code for processing. So you can see item and display string I already process. So I need to also now process array items. Okay. So we assume that there's only one expand. We should also assume that there's only one array items. So let's do that. Expand.m array items. If it's not equal to 1, return. This essentially means return error because the NatVis entry is initialized in the error state. Okay. We should also assume that there's only one size and only one value pointer. let's see, const natviz data array items equals expand.m array items 0. There's only one. Okay, so let's do this again. If array items dot m sizes? Maybe I should call this size, because there's only one. Yeah, array items. Array items, we'll keep it plural because the class name is plural. And there are multiple array items, logically, if not literally inside this node. Okay. So there should be one size and one value pointer. Good. One size, one value pointer. Array items dot m size 0. Let's do this. Value pointer. Okay. So the inner contents of size and value pointer, the inner text, will be expressions that we have to evaluate, and fortunately we have code to do so. If we ever can't evaluate code, we get an error, then we must return an error in evaluation in any of these expressions means that that's an invalid visualizer, and you should go to the next lower priority visualizer. Okay. So we're going to evaluate the size inner text and get a size value and get a size result. Okay. Evaluate the size inner text. All this stuff is the same. Size value. Yeah, actually all this stuff is the same. And then we're going to do the same thing. Except we're going to say value pointer. Just trying to make sure I don't control D another size, because size is a very common name. I just want to make sure there's not another word size in this code that I don't want to replace. Okay. So now, thank goodness I wrote all that other code that I just relied on to evaluate this expression. Evaluate expression will actually look at these intrinsics. Intrinsics is like defining a little function inside of the native visualizer called size that you can refer to from other places. Here it is referring to size in order to calculate the display string. Here it is referring to size as part of the size. So this size evaluate expression is going to call this size, which the first thing that evaluate expression does, evaluate expression, is look through the intrinsics to see whether there's one that matches this guy right here. Okay? And if there is, then it calls that intrinsic, which in turn is an actual evaluate expression in class scope, which calls the Clang stuff that we looked at before. Okay. So, boom, we actually have both values now. What do I do with them, actually? I have to return them somehow as part of the natviz entry. let's take a pause here, compile this, and oh, I actually can't assume this, that there's exactly one array items. No, array items is optional. Of course, array items is optional. Okay, I should say if array items is not empty. Okay. All of this happens if array items is not empty. Then assert expand.m array items.size equals 1. Wait, no. I don't want to assert this because this is like customer data and there could be a malformed NatViz. So what I actually want to do is actually it's the same exact code that I had written before. I'll just recreate it. If it's not empty, then it has to be 1. Otherwise, there's an error in processing the native visualizer. Ideally, I would have some kind of log here. I would be like, native visualizer failed for such and such a reason. That's complexity that I'm avoiding for now until I get around to, that would be like a feature request. I made a bit of a product decision when I started this feature that I'm loading the Visual Studio native visualizers as they are. I'm not yet supporting, like I'm supporting loading existing native visualizers from Visual Studio. To make things easier for myself, I'm not yet supporting loading arbitrary native visualizers. For example, if I look through the Clang source, oh, it's called LLVM. If I look through the Clang source code, there should be a NatViz file somewhere in here. This will probably take a while. It's very big. Okay, there it is. You can see that Clang ships with some native visualizers, right? So the Clang developers created their own Clang utils. Let's go take a look at them for curiosity's sake. Clang developers created their own native visualizers because they created their own complex data structures that they wanted to, there it is, that they wanted to have an easier way to see. And okay, so here they are. Type native, interesting. Okay, so Clang type, display string, they have many display strings that display and many, so this is, Clang type is like their equivalent, this is a type, this is literally a type, okay? So remember, oh, I should actually install this in my Visual Studio, this would let me see what Clang is doing, but if you recall, we were trying to look in the abstract syntax tree and it was difficult to see what was going on in there. This visualizer solves exactly that problem. So if I install this visualizer, I should have a lot easier time telling what's going on. So this will show exactly what is inside any type. If it's a built-in type, it converts it to built-in type and then shows that. If it's a pointer type, etc. So that's pretty cool. So different projects often create their own native visualizers at the moment. And in that case, the person designing those visualizers, writing that XML that you just saw, is going to want to have some indication of when they mess up what went wrong. And so they're going to want some logging here that says, hey, this is how you messed up. This is what you need to change in order to fix your visualizer. Again, I'm skipping that complexity right now. I'm focusing only on the smallest possible thing that can be useful to somebody, which is load the Visual Studio visualizers and show them. And right now, I'm focusing on the smallest possible thing that can be useful to me to get something on the screen which is stud vector visualizer. Everything else in this file I'm not focusing on right now. I'm just focusing on stud vector, Visual Studio 2015. We're going to write the things that are needed to show this and nothing else. Just to make my life easier. So, oops, I meant this. So this is what we need to do. We need to take this size value and value pointer value that we just parse the value of. I'm going to compile that and make sure that we're actually getting valid data out of that. I'll put a breakpoint here. Wait for this to compile. Come on, buddy. Here we go. Put that breakpoint there, press run button. Here we go. We have a valid size. We have a valid value pointer. We're going to evaluate those expressions. We got a result. We got a value. The size is 1. Very good. Very good. The type of that size is an N64T. Perfect. Everything's good there. So the value pointer should be of type pointer. It's an Int32T. Interesting. Did something go wrong? Nope, it's okay. Oh, is it a pointer to Int32T? Hello? No, it should be a pointer to the template argument. Uh-oh. Uh-oh, I think we may have hit a snag. Oh, no, it is a pointer, but it's a pointer to Int32T. Interesting. It's not a pointer to the... Oh, wait, no, Int32T is my pointed type. Yeah, of course it is. It's a vector of integers. Or wait, where am I looking? Let's just load it up here. Types. This is the file that I was looking at. It is a vector of integer. And int is an int32t, so I think that's okay. If I had a vector of string, though, would it work properly? Would this type be a pointer to a stud string instead of a pointer to... Would this say stud string here instead of int32t? I wonder. That depends entirely on how I construct the fake class that I construct. So let's go look at that. See, like, this is an N32 anyway. Pointer to my first. Let's go look at the actual vector class. Let's see here. My pair is a scary val? What is a scary val? Class vector. Oh, this is the vector bool specialization. Okay. Yeah, they have a lot of optimizations in the actual vector class that make it difficult to tell what's going on. I have learned that _ty is the type. Everybody else just uses t, but for some reason they use _ty. They must have built this way before that t convention was actually a thing, right? Oops. So my question is, why are we getting a different type? You know what I can actually do? I can just find a vector somewhere. Here's a vector event. You have a myPair, which is a myval2, which is a myFirst, myLast, and myEnd. Actually, you know what I should do? Let's see what it does for a vector of stud string. Let's see what these types are. I'm relying on the types of those things. Okay. So vector of string. myval2. What are you? Yeah, look at that. myFirst looks to be a string. What is the type of myFirst? Copy value. I don't know. Let's do this. Copy. No. Can I hover it? Just tell me the type. Tell me the type, please. Come on. Tell me the type. 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 Oh, I'm sad. I just want to know the type. The type. Damn. Alright, I may have to actually just read the class. Let's do this the old-fashioned way, by reading code. Okay. Here we go, it's going to be an adventure. Oh. So we want this scary val. Scary val is a vector val. Vector val. Pointer. So the type is pointer. Pointer is val types pointer. So we want the template argument of vector val. Which is a conditional. Is the simple allocator or who knows what that even means? Simple type. It's probably this. Yeah, it's probably this. Okay, I think I'm gonna get it. Here's why. When a program is compiled, here. Right now, what I'm doing, whoa, let's put that back over here. Right now, what I'm doing is I'm pulling the type, the appropriate type, for this variable out of the program I'm compiling. And so, and I'm putting that type here, like where this comes from. Let's go back here and look at the generated code for my fake expression. And here it is. Okay, where does this come from? Is the question. And I'm pulling that from the program that I compiled. And that comes from this should be the same type as the argument of vector. You see, I don't actually have a template class vector because it's a fake class and I didn't need the template, so I didn't put it there. I cheated. I totally cheated, folks. Okay? The real class vector has a template argument. I don't, because I'm cheating. It's the greatest. And I was worried that would bite me, that it's choosing int32t as a default. Okay? But actually, I can get away with not having a template because I pull the appropriate type of all of the variables that depend on that template argument out of the program that has already been compiled. So my bet is that if I do this on a vector of stud string, it will pull stud string out of the program that's being compiled, and this will say stud string like it should. So I don't think I have a problem there. So what I need to do, so then where was I? Oh, I remember where I was. Okay. Evaluating expressions. We jump down here. Broop. Okay. Value pointer should correctly be a pointer to an int32. Pointer to the thing that is pointed to is int32t. All right, and this is a vector of int32t, so we should be good to go here. And then the actual value of that looks like a pointer to me. All right. So the next step we need to do is store this somewhere and display it in the UI. Here we go. Where to store it? So this is a NatViz entry. Is like the compiled NatViz that is valid. Well, it defaults as error, but you know, the evaluator evaluate visualizer sets it to OK at the end and returns it. Okay, if it's valid, and all of the information needed to display the visualizer to the user is contained in here. And so I need to add the array information here somewhere. Problem is it's optional. Not every native visualizer has an array item in it. So what do? I'm going to need to store this size value and this value pointer value in an optional. This is like the definition of what stud optional is for. Struct NatViz array items final. I think this is what I do. Size and S and first. Okay. Array items. Boom. So I just do this. Oh wait, I shouldn't have moved this inside here. Okay. NatViz entry dot array items equals, I forget the stud optional. What is the syntax for stud optional? Actually, I'm just going to go ahead and compile that and see whether I get a crazy error. I think I probably have to do this. Oh, maybe I didn't have to do that. Well, I'm going to leave it there anyway, because why not? Okay, cool. So we have a stud optional, we have a constructor that takes the okay, we have an in-place arguments. Oh, okay, we have a, let's do it that way. NatViz array items, I think this should work. Size value and value pointer value. Will that work? Was that valid stud optional syntax? Yes. Cool. Let's go to the processes panel. I completely rewrote this code in the last couple of days. It is now way nicer. What happened is I got to literally the point where I am right now, okay, a few days ago. And I realized that if I wanted to add the feature that we're adding right now to the processes panel code that I had before, it was going to cause like the problem was that in the processes panel, the logic for displaying a tree and what should be in the tree was meshed together. It was all intermingled in the same class. And it was just a mess. It was getting increasingly difficult to modify to add new features. So I spent a few days tearing it all apart, and I created a GUI class tree.h where you can actually add nodes to a tree, and so the logic of how to display a tree and the logic of what goes in the tree are now separated. Okay, this stuff you see on the left is the logic of what goes in the tree. It is no longer just right, and now I can use this to make another kind of tree if I ever want to do that. You know, I'm normally against premature abstraction. It's like as bad as premature optimization, possibly even worse. It's like a premature unoptimization a lot of the time. Except in the case that you're preventing yourself the future cost of having to maintain code that is just disorganized, right? I support abstractions that help you organize your code, even if they're not, like, the only tree in this application is the processes panel, right? So I originally wrote it, I was like, this was a mistake. What's the harm in just including I don't think I'm ever going to have another tree. I'm just going to write a processes panel that is its own tree. And that was a huge mistake. I should have started with having a separate tree class. And I paid for that mistake over the last few days when I had to rewrite the whole thing. Okay, so somewhere in here, we are going to have the spot where NatViz items are added. Here it is. Okay. So this is saying update node. This is like a node of the tree that is a symbol. And update its children. In other words, add all the children that it should have. For each item in the tree, we added item here. Okay. Oh, so then what I have to do is I have to say if natviz entry dot m array items. It's been a long time since I've used stud optional. I don't remember. Is there a... Yeah, okay. Then... oh. Okay, so now I have to do something like this. I actually don't know what goes here, but I'll write size t for now. Size equals natviz entry dot m array. Is there an arrow? Oh, there is an arrow. Oh, so it's just like a pointer. It's basically like this. It's like a fake shared pointer, but it's optional and it's never shared. I think I could just, I think I could just treat it. I think they semantically want me to pretend like it's a pointer. That's how set optional work. I actually haven't used it that much. If so, that's cool. I like that. And it will never leak. Okay, value. No, size is what I want. There it is, size. And size is an evaluation value, which needs to be, and it's actually, an evaluation value is actually a buffer of bytes, which contains actual data, and type information about the thing. And I don't have the type of compile time here. That's the problem. I don't know what to write here. I don't know what type the program. So here's what I'm going to do, actually. Assert natviz entry.m array items arrow m size.m type. And then I have to look at what I can do with type. Dot get size. Oh, I have to say I want to know whether it's an integer type. Oh no. Oh no. I think I have to write a function for that. Okay, well, fine. Bool is integral type. Const type. Reference type. Okay. Where was I? Is integral type. Type. So it should be an integer. Oh, wait. This should be inside here. Yeah. Yeah, because if somebody tries to give me a type that's not an integer, then I can't interpret an array with it. So if it's not an integral type, then I have a problem. I think I have to say engine, : here. If it's not if the size that they gave me is not an integer type, we fail. Okay. Okay, so now here I can assume that it is an integral type. So now I just have to make sure that the size of the integer that I'm putting it in is no smaller. So I'm going to say assert natviz entry dot array items arrow m size dot m type dot get size. We know it's an integral type. Is let's do size of size t is greater than or equal to this size. So if that's not, there's also like a signed unsigned thing that I have to worry about, which only matters if I have, how big is size t? It's like max size t is like, no, that's not true. Maximum size of size t, maximum size, max in 64t. Tell me the number. Here we go. Size t. Oh no, I just had it. This. Okay. Half of this, which is basically this. Okay. Am I ever gonna have values bigger than half of this? Is the question, or negative values, right? Like, the answer is if that is the case, then I have a bug somewhere. Right, and so if I were writing systems level code where it's super important that I never mess any of this stuff up because it might be powering an atomic reactor somewhere, then I would worry about this. Okay, if I don't worry about signed or unsigned, signed versus unsigned types here, then this will break if my customer ever has a value, ever has a vector containing more than this many things, or more than half this many things. More than this many things. Which is not possible. To have like a vector that would be literally half of the entire virtual memory space, and there's not enough physical memory to store that much stuff. Is there enough disk memory? Is there like a degenerate case where a vector could... No, I'm going to go with no. It's just not possible. Okay. So, let's do this. Size T, size. Oops, size. We'll write an error message right here. This is a pretty large array. So I'm going to write the but I'm still going to write a boring message. I'm not going to write a message like, this is not possible. Okay, the message should be size type not large enough to store array type, to store NatVis array size type. That doesn't make a terrible lot of sense. Size type bytes not large enough to store NatVis d bytes. Size goes here, and this expression goes there. Okay. So now I have a special function, buffer to type size t, and I give it msize.mValue. Boom. Now I have the size. Now I can say, okay, great. Okay, so now I have the size. So now I can do this for size tk equals 0. K is less than size. K plus plus. Okay, here we go, folks. Here we go. We're gonna make a new entry in our tree. This is the code for making a new entry in the tree. Boom. Let's just, for now, we have to capture K. Let's just see it working. So we're gonna say stud2string K. Okay, that's fine. We'll get rid of this for now. That's fine. What's going on here? It's making a new NatVis item node private. Oh, wait. Yeah, NatVis entry. Oh, I think I have to make a new NatVis entry for this? Only if it's expandable? No, I know what I have to do here. So the original NatVis entry, yeah, this should be fine. And I have to make a new name. So this is what I'm going to do. Stud2string. Okay. I key off the name that I put here to tell whether or not, like if the array adds or removes entries, whether or not I need to update that entry. And so I'm gonna put like a unique thing here that it's not likely to be given that name in the, it could be given that name actually. No, this is actually the name this is the name it's supposed to be given, yeah. Microsoft isn't going to give it this name because their debugger automatically generates names of that value. Okay. Cool. Oh, it's not actually going to find this, though. I'm going to have to write some other code. You'll see what I mean in a second. I have some other code written in here, but it's not going to run that code on this, I think. Yeah. Yeah, I'm going to have to update this code for what I just wrote. Yeah, so he's looking for that item name. Why does it have to recompile everything? I don't remember changing a major header file. Did I? Did I just? Oh yeah, I changed types. What did I do in types? Oh yeah, I added this. Okay. I changed the types header file, so I have to recompile everything. Didn't take that long. Buffer to type is a member of common. Or no, it's a member of engine. That's weird. It should be a member of common. Should it be? This should be in common. Well, it does depend on type. Okay, that's why it's in. Good part of it could be moved to common, though. Okay. It's an engine. That's fine. Common is my directory for header files that could be used for any C++ project. Engine is my directory for files that are specific to this debug engine, this debugger. Not that I have another C++ project that I'm using right now, but it just helps me organize stuff. Okay. We just have to implement this is integral type. Should be no problem. Bool engine : is integral type. It would be really nice if in Sublime, when you are auto-completing, it looks at what's open on the other side. Because I always do this thing where I have all the headers open here and all the CPP open here. And like, is integral type is right there. If it could just find it and auto-complete for me, that would be great. Whoever makes Sublime, get on that. That's the feature that I want. Okay, is integral. So, if types basic type equals get definition types basic type, return basic type greater than or equal to basic types basic. Do I consider char to be an integral type? Oh no. Oh no. Stud is integral. I'm just going to do exactly what C++ does. Yep. Provides, if T is the, oh wow, bool is an integral type to C++? Okay. If you say so. And basic type less than or equal to uint64 types basic uint64. Great. Otherwise false. wchar t is an integral type? What? C++. I'll bet it gets that from C, honestly. That seems like the sort of thing that Dennis Ritchie and what was his name Kernighan. Those two did back in 1972, and now C++ is saddled with it. Booleans and WKRTs are integers. Okay. Sure. Sure, bud. Suits me just fine. Of course. Get type definition. I'm forgetting the word type all over the place. Cannot convert. Oh. Okay. 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 Let's give that a try. So, processes panel. I'm gonna run through the code in the debugger before I am brave enough to just let it run. I'm gonna walk through it, see what it does. Oh, yeah, see? See? See what I mean? Okay, yeah. Oh, we got an error. Wait, how did we all of a sudden get an error? We weren't getting an error before. Oh, it defaults to error. Okay. Oh, right. Right. I'm silly. I was being silly. Okay. We need to say size value. We haven't actually set this value yet, and we're trying to access it. Easy fix. Okay. Let's try again. Okay. What? Oh, it's because I have to press this. Okay. Here we go. Array items is not null. Cool. Good. We're big enough to hold it. We got no cert. We're going to get the size. Size is 1. Size is correct value. Okay, cool. This looks like it's working. We're going to add a new node. Oh my god. It says 0. Okay. Oh, that feels good. And it will probably... Oh, great. Good. So this is what I was talking about before. It doesn't know how to dedupe these yet. Every time I take a step, it adds new ones. And I need to write code that I haven't written yet to dedupe. See, first it added 0. And then, for some reason, added another 0. And then it added 0, 1. Oh, it added 0 twice. And then it added 0, 1 twice. And then it added 0, 1, 2. And it's going to add 0, 1, 2 again. And then it's going to add 0, 1, 2, 3. Yeah. And so what I need to do is detect if I've already added this 0. Don't add it again. Don't have to add it again. You can just not add it again. So anyway, we are actually off to a very good start here, though. We just need to look for this name. And let's see. I think this is where we do it before. Yeah. This is where we were checking the name before. So we just need code like this. We need literally this exact code. Let's make a helper function. Find natviz item child node by name. Here's the node we're looking through. Here's the name. Just gonna move that there. Result. Return result. Find natviz child by name, symbol node. The name is name. We need to get rid of this and say name. Name. Great. If entry continue, entry. Oh, so actually I can just do this. Okay, that code is now much simpler. And now we can do the same thing down here. Okay, this time I'm going to construct the name out of the K variable. Stud string name equals K bracket K bracket. Just put the name right there and then right there. All right, that should solve the duping issue. Still will not solve the formatting issue, also known as it is ugly. Node is what I called it. Node. Okay. Okay. I'm so excited. Okay, open it up. We have a 0, and then a 1, and then a 2. Yep, that solved the deduping issue. Okay. However, we have not solved the fact that there's no context here. We can't really tell what it means. Actually, I do want to test something though. This should, my theory is that this should all work properly if I swap this to be a vector of stud string. There's no reason this shouldn't work just fine. I don't have a visualizer for stud string yet. That's the part that won't work. But the type should show up as stud string. Put the breakpoint here, run it. Vector of stud string. Oh no! It didn't identify the visualizer for it. Okay, well I guess I can't test this today then, huh? Oh, sad. That's unfortunate. Why wouldn't it recognize the visualizer for vector of stud string? Oh, I can't imagine. Well, too bad. We didn't get that one for free. I was wrong. Okay. So we have to make this look a lot prettier. Let's start here. So this is where we set the default name. I try not to rely on it too much because it will get overridden in the update function. Okay, this is just like the initial name. I could make this empty if I wanted to, but I don't because it helps me to debug if there's actually some kind of string in there. in case I don't call the update function, or in case I'm looking through code where the update function hasn't been called yet. And in this case, I'm not calling the update function yet, so you can see, yep, there we go. So this looks a lot nicer. So, but then the problem here is, I'm gonna write some different code, which is different, entirely, what's the word? Vector of int. Entirely idiomatic way of using a vector. I'm going to write this. I'm going to change the value after it is initially written. And I think that this will not work the way it is right now because it's not updated. After the value is initially created, it never gets updated or refreshed again. Okay. So that breakpoint right there. Open up that bad boy. Okay. Here we have a value of 0. Oh, I wrote 0 with 0. Wait a minute. I pushed back 1. Okay, push back 2. Am I mistaken here? I pushed back a value of 1. It should say 1 there. I pushed back a value of 3. It should say 3. It says 2. Oh, I know it's wrong. It's obvious. I'm stupid. It's obvious. I put K here. What I should have put is, let's see, I have a perfectly good value that I have to pass in. So natviz entry array items. Oh, I can't even do this here. Yeah, I can't even do this here. Because I don't know what the type is at runtime. I can't do this value because I don't have the the type is here. It's a runtime type. Okay, here's what I can do for now. ToString. I have this nice ToString method. Okay, it's not perfect, but it will take a type and some memory, and actually, let me use buffer to string. This is temporary because this will not print the right thing if it's a complex type. For example, a stud string or anything else. Okay, but I can use value type, value. I think this will work. Will it compile? No. Whoa. Value is not a member of... Oh. Yes, it is. Oh. Oh, that's right. So it's not even enough. Oh my god. Okay, here's what I have to do. So the thing that the value type is not actually the type that I want. The value type is the first element of the array, which I then have to increment by the size variable times k in order to get the actual item in the array. Okay. What I'm actually going to do here is just call it name. This is all really complex stuff that should be done in an update function. Get rid of this capture. Okay. Entry name. Natviz entry name. Okay. We're going to add the update function in here. We're going to go there. This is where it looks up the natviz entry item. Okay. This is what's going to fail. I'm going to get this assert right here. Here's why. For the other two, capacity and allocator, they are represented as natviz entry items that I can look up in the NatViz entry. Okay. They're going to be in this list right here, expand items, which I'm looking through right here, expand items. The ones that I'm creating now are dynamically generated. They're dynamically generated from this list. And so it's not enough to look through this expand items list. I also have to detect whether it's a dynamically generated item. So I have to write some additional code. Should be too hard. Types, put the breakpoint there, run, open this up, boing. Okay, good, exactly what I thought. It can't find it in this expand items list, which is fine because it's not there. It's not capacity or allocator. It's dynamically generated based on the the array starting location and size. Okay, so I have to write new code here. This is going to be if NatViz entry item do all of this. Well, hold on. I don't know how much. Where do I actually use? Oh, all over the place. Oh no. Oh no. Oh no. Okay, actually I'm hoping I don't have to duplicate most of this code. How much do I need? I need the type. I get a lot of NatViz entry item value type. Yeah, and the value and the name. Type, name, and value. So maybe I can actually do this. Engine, type, item type. Value is a, I think it's a buffer, item buffer, and a stud string item name. If that's ugly, I'm not going to do that. I'll keep them on different lines. If this exists, then the item type is NatViz entry item value.mtype. Item buffer is NatViz entry item mvalue.mvalue. Item name is NatViz entry item mname. Okay. Otherwise, oh, and then I have to start replacing all of these. Okay. Okay. Item type. Cool. I think this should be the only place the value is used. No, there too? Okay. And the name, that's the only place the name is used. All right, so if there's no entry item, then we have to see whether this is a dynamically generated item. So first we're going to check whether the NatViz entry array items exist. If they do, and otherwise we definitely have an assert. Assert false unknown NatViz item name okay. So the name, the fake name that I made for the case where there is a an array item is square bracket, number, square bracket. So what I'm going to do is stud string number index equals item name dot substr 1 comma actually I'm just gonna say 1, and then I'm going to call stud s2i. What is it called? s2i. Stud a2i. No, s2i. Yeah. Stud s2i. And I can just say int index. Okay. I guess I have the problem here of like, what if... Okay, this is what I'm going to do. Assert common begins with or starts with. I was thinking it looks weird. Just to make sure that I'm formatted correctly. Array item name should start with square bracket. And then we'll also ends with. This is just some sanity checking. It's always a good idea. Array item name should end with end square bracket. Okay. So now we know we have the correct format string. We'll get the index out of it. Let's just run that code and see whether that works. I should be able now to put a breakpoint right here. Did we compile? No. Oh. Yeah. I'm not really sure why there's a difference between arrow and dot in this language. The only thing it ever does is cause me compile errors like that. Should just be the same thing, my opinion. Okay. 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 Open that up. Whoops. Oh, I forgot. I forgot to actually put the breakpoint that I was gonna break to step through this code. Oops. It definitely stepped farther than I wanted it to step. Can I save this, or am I gonna have to run it again? I'm gonna do a sneaky trick. Pay no mind. Pay no mind to the man behind the curtain. Oh, oops, okay, that sneaky trick didn't work. Sneaky trick to try and save my debug session without having to reboot it. Okay. Now. Oh, I should be able to put this here. And as soon as I press this button, boom. Item name is :0. Great, this is the thing that we just added to our array. And I should get the trivially correct value of 0 back from this function. The trick here is I actually sent it a string with a square bracket on the end. Don't tell anybody. The s2i function actually just ignores everything that's not a number. And so I believe I get a, yeah, it just calls str2l, which ignores everything that's not a number at the end. So I believe I just get a correct value and not, I think 0 is also the error code return value because this implementation is not great, but I think it's correct. Okay. So we have an index. We also need to get the natviz entry array items Let's see here. So we actually don't need to know the size anymore. We just need to know this. Okay. All right. So I'm going to lie to the compiler. Pointer. No. It should say object. No, element. I'm going to lie and say that it's actually a pointer to a uint8, which is not true. Buffer to type uint8 pointer array items arrow m first dot m value. First element. So now we have a pointer to the first element, and we can get uint8t star this element by first element plus index times the size of the type. So I need to, and this is all very difficult to deal with. Let's do this. Natviz array items. We'll make ourselves a little shortcut. Natviz array item. Oh, I can do this. Oh no. Okay, I only use it here so far. Fine. There. Does stud optional support casting? It does. Look at that. It's like everything that I want. It's also some template mess that will probably slow down my compile times, but I don't really care that much. Index times natvid array item arrow m first dot m type dot get size. No, I can't do this. This will be a pointer to, this will be a pointer type. So no, I can't do this. I have to get the type that it is pointing to. Okay, this is a little bit more work here. So this type is a pointer type. Okay, it's going to be types pointer, probably engine types pointer, probably const engine types pointer, pointer type, a pointer to my actual element type. I want to know the actual type, not the pointer to the actual type. So I'm going to get type definition okay, of that type. It is a pointer type. And then I can make an engine : type element type equals pointer type pointed. Pointer types are just the type that it points to. This element type is the thing that I need the size of. So where did I screw up there? Cannot convert from optional array items to const array items star. Isn't that exactly what this is supposed to do? Oh, this is operator star, not operator conversion to thing. Oh yeah, it's the pointer dereference operator. That's silly. It's not a type conversion. And it's probably not going to let me make that type convert. Oh wait, returns the value. Is there a casting operator to a reference type? I'll just do dot value. Okay. Dot value. And now I can make this a reference type. And now I can copy this. And do this. And replace it with dot. Alright. Fix that problem. Fixing problems here tonight. Let's do it. Conditional expression of that type is illegal. If... Oh, yeah. Right. Fine. Don't get snarky with me. Alright, so the operator class is not exactly what I would have hoped for. But, oh well. Really wanted that pointer conversion type. But of course, I mean, I guess it makes sense that they're not going to give it to me. Why would they? They really don't like raw pointers to things over there in the C++ standard committee. For good reasons. Get type definition, no matching overload. Oh, right. Get type definition has a template argument. Buffer to type. Undeclared. Oh, this is an engine buffer to type. Okay. So I'm lying that it's a pointer to uint8t. It's not a pointer to uint8t. It's a pointer to my actual element type. But that's okay because I'm not going to actually reference anything in the pointer. Like in the actual program, this is a pointer to the actual element that is in the vector that I'm trying to access. But I'm just going to pretend it's a pointer to u8t and do the math myself that the compiler normally does. I'm just doing that math here on my own. Using the pointer math for uint8t. This is actually, if you have a pointer to any type, this is done for you by the compiler, this step right here, the multiplication times size. However, uint8, and it's being done here actually, in this pointer addition, it's being done. There's an implicit multiply times the size of uint8t, and that size is 1. Multiplying times 1 does nothing, which is why this works. Okay. All right. We got the pointer type. It is not null. I should add a check to make sure that it's not null. I'm crazy about asserts in case you haven't noticed. Pointer type. Oh, this check should go again in here. Wait. Is that true? Vector bool. Oh, see, bool. No, because this is a value, whereas this is a value pointer. Okay, that's fine. So a value pointer should always give you a value type. Size value. Okay. Value pointer type should be assert. Oh wait, no, not assert, of course. If it's not a pointer, return an error. Cool. So now I can just assume it's a pointer here. I'll just assert pointer type. Because why not? Asserts are free, people. Free. And they're the greatest. Type expected a pointer type to be. And we're going to need to, just like a get name. Yeah. Engine, get name. Dot C string. Cool. Now where were we? Okay, so we get the type that is pointed to. This is an int32. Perfect. Size of int32 is going to be 4. And so we're going to get the index. Index is 0. First element is... Okay, we're just going to add 0 to... Okay, this all looks like it's working properly. I'm going to continue writing. Okay. So I have the address of the thing that I want to print in my debugger. Type name. Okay. Type item. I need to fill out these 3 things. Here, the same like I did here, I need to fill them out here. Item type is easy. It's going to be element type. Done. Okay, that was easy. Item buffer is trickier. Item name is easy. Item name. Actually, I don't even know why I have item name in retrospect. What do I use it for? Can I just say item, yeah, I'm just gonna put this here. I don't need, okay, I'm gonna delete that. Delete that. Delete that. Cool, great. So now I just have to figure out what to put in this buffer. Because what I put in the buffer depends on what the type is. Is that true? Can I just put a pointer? Where do I use the item buffer? Oh, it's looking for an address. It is looking for an address. Okay, great. Then I can just do... Okay, watch this. I have the opposite of buffer to type. Engine, type to buffer, item buffer, this element. I should call this element address. Element type, element address. It's so easy. In fact, item type. I don't even need to make this temporary. I'm simplifying my code here. Should I combine these two? Should I do this? Yeah. Element address. Cool. I think that might do it. And then from there, the rest of the existing code takes over to display the visualizer. Value pointer.m type. What are you? What code are you? I didn't modify this code. Did I? M type is not, oh, I probably did. Okay. Value pointer. Dot value. Okay, this is what I want. What are you? Why are you code? Okay. We're super close here. Very, very close. So that should be enough to update me as I go. Okay. Pointer type. It's valid. The item type is element type int32. Int32t. Item buffer is expected to be a pointer. Always, I'm pretty sure. Because item buffer is turned into this address here. It's expected to be a pointer here, but not here. Here it's just a regular item. That might cause problems. Hold on, let me think this through. If it's a... Generally what I do is if it's a user defined type, like class or struct, then I store it in a pointer. And it's like the pointer in the debugged program's memory space is what all these pointers are. But if it's a basic, if it's like a fundamental type, then I just store it in this buffer. So this is expecting a pointer, and this is expecting a fundamental type. That's the problem here. You're never going to have a visualizer for a fundamental type. So find visualizers for type name if it's a fundamental type will always return empty. And so this code will never get run. So I think we're fine. Okay. Good, because it's an integer, so just like we said, there are no visualizers because it's an integer. Oh no, it's a pointer to an integer. Oh no. We don't want a pointer to an integer. We want the integer. Oh no. Okay. So this is going to convert that into buffer to string. Yep, buffer to type. It's going to assert because it's the wrong size. It didn't assert. Oh, okay. They happen to be the right size. A pointer to a what is t in this case? Hello? A pointer to this integer. No, this should be 4. This should be 4 byte. Buffer size is 8. Size of t. This should have erred. Am I blind? Am I reading this wrong? Hello? Output. I didn't break debugger. Should have had a log. There it is. I don't know why it didn't get stack trace, assert failure buffer to type. Okay, yeah. I don't know why the debugger didn't. Okay, well, anyway, I'm gonna ignore that for now. I'm gonna return this. Turn this to string. Yeah, it's just a crazy number. It's like obviously wrong number. Because it's an address to the actual number. We're gonna set that text. It's not expandable. And there's the crazy number. Okay. Okay. So I think for now, I'm actually just going to do the hacky thing. And say... type to buffer. uint8 t star element address equals. Okay. We're going to do the hacky thing and we're going to say if your user defined type then store you as a pointer in preparation for getting a visualizer. Otherwise, store you as the actual item. I think that's all we can really do. Get. So if, because this is my program's internal convention. Because if it's a user-defined type, I don't want to pull a potentially large chunk of memory out of the debugged process and store it in my process. I want to minimize the amount of transfer of copying of bytes that goes back and forth, right? So I really just store the pointer, and I say if you want to get the actual data, then you have to, you have to go back to memory and do a memory query and get that data. But for basic types, it's just basic type. It's just like 1 byte or something, 4 bytes, 8 bytes. 8 bytes is pretty much the largest basic type that you're going to get. So just store it in the buffer. And you're never going to have to go back to memory. So I think what I'm going to do is if get type definition types user defined. So what's it called? User defined item type. In this case, we do this. What we were doing before. Store the pointer. Otherwise, I now have to do a memory lookup. Where else do I do a memory lookup? Just going to copy this. So the memory range will be the element address. I have to get the item type size. So this is the memory range that we're going to query. What is this called? No, you know what? Item buffer. Item buffer. Memory range. I think I could say M process ID and M memory accessor. And then what to do if I don't have it in memory. If I don't have it in memory, actually, I should just... If I don't have it in memory, this value should say something different. I wonder what Visual Studio does. Let's see. So we're going to do something crazy here to test what Visual Studio does in this instance. We're going to come right here. We're going to open this guy. We're going to go to the raw view. And we're going to change it. Boink, I just broke this vector. Unable to read memory, it says. Unable to read memory. Yeah. Okay. So if I do a memory access and it's okay, everything's good. If I do the memory access and so there are three possible values. Invalid means that like you tried to access the null pointer or some kind of protected memory, it couldn't get anything. Not present means, well, the debugger just doesn't know what it is. Hold on, I have to go get it, ask again later. Okay, and I have to display 3 different things in those 3 different situations. So I'm actually thinking that this value, string value, should be maybe I should do this. Item type, item buffer. Item type, item buffer. Okay, let's do this. Stud string fundamental value. Okay. Fundamental value equals, and then we'll do this. We'll just do this thing up here. No. We'll say display value. It's kind of what Visual Studio calls it, display value. Display string. Display string. Display string equals display string. Display string. Display string. Display string. Display string. Item type we already set. Item buffer we already set. Else if result equals engine memory access result invalid, display string equals invalid. This is the equivalent of Visual Studio printed what we saw before. Else display string equals ... Well, that's kind of gross. This is way more complicated than this, but that's okay because we're doing a bunch of work. In this, the work was already done somewhere else. In this, we have to do additional work. But I think we have now done it. I think we should have a working thing now. It's like the third time I've said that, of course. If we encounter no other problems, I'll have a working thing now. This is just a weird syntax thing. Types is not a class or username. Engine types. Okay. Let's try it again. Is my breakpoint still there? Good. Right. Good. Good. Boom. Pointer type. Item type. We already know that's correct. Index is 0. First element. Element address. It is not user defined, so we have to look up the actual value, which will be an integer somewhere in the memory process. We use this memory accessor, which is a lambda that was defined in a way different place. Where was that lambda defined? Yeah, way somewhere else. Let's look at it real quick. This is the sort of thing I want to get rid of with my debugger. Calling through all these. I actually have a prototype of a feature that would let you bypass all of this stuff immediately. Okay, so here's the memory accessor that we're using. It just goes to the memory cache that has already been populated. And if it's not present, it fetches the memory for us. Oh, perfect. It's so easy, so beautiful. I love it. We'll step back through all this stuff. Okay, get the result. The result is not present, so we display ... It's already been fetched for us. When it's finished fetching, it will update automatically. That makes total sense because it's the first time we've tried to they must have allocated this vector element in a new page, so we should probably get this again soon. Yep, we get it again. This time we do the same thing and we get access okay. It fetched it. It told us to refresh. We refreshed after we got it. And now the display string should be a number 0 or 1. Well, that was surprising. Oh yeah, it's 1 because I pushed 1 onto the buffer. 1. I pushed 1 onto the buffer. It works. Yay. There's no visualizer, so it just uses the display string. It sets the text to item name : 1. It says it's not expandable. It works. Okay, now if I F10, it should update it to 0 because I have vector event 0 equals 0. I push back 2. That worked. And then I set 2 to 0. Oh, it all works so beautifully. Oh, what? Oh, oops. Okay, that's just a bug in my program. I don't know why the debugger didn't catch that. Oh, because I have to press retry to debug the application and then... Okay, cool. Well, great. Should probably fix that bug. 0 equals 0. Or no, 2 equals 0. I think is what I wanted here. Anyway, it works. Okay. We did it, kiddos and cadets. All right. That was a lot of coding, but I think we have a fully functional feature now. Let's go back into it so we can look at it as we talk. We now have a native visualizer which can understand simple arrays and therefore understand vectors. And I think I've programmed everything that is needed except for the allocator. That's just a different object to load and display a vector of ints. There it is. We don't have a vector of hello. We don't have a vector of strings yet because for some reason it's not recognizing that allocator in the string search. I think I know why. I think it's because string is a vector type and that's confusing it. But we'll get to that later for sure. In the meantime, it appears to work. Yeah, all of these values are correct. So this is an important step for me to make sure that my goal here is to make the debugger usable by me to debug my own program. I can't ask anybody else to use the debugger if I can't effectively use it myself. And I use the stud stuff all the time. I use stud vector, I use stud string. Every so often, I just use a stud optional you saw. Every so often I use a stud map or a stud variant. And I use a lot of stud any. If I can't see the insides of those things, then I can't use my own debugger. So this is an important step for me to be able to use the debugger. Once I have all of these basics in place, I can see all of the standard library stuff with the native visualizers. I did a search in file, let's see, feature before, okay, and this works okay too. Once I get all of these basic elements in place that I can use to use the debugger myself, then I will do another alpha. And you can join that alpha if you go to luxdebugger.com. You can try all these features out that I'm implementing. You can give feedback straight to the developers. And if you do, you get a discount when the debugger is finally released. So that's it for today. Thanks for joining me. We do this every Tuesday night. We will be working on something else fun and interesting next Tuesday, and I haven't decided what it is yet. So come back on Tuesday nights in order to see the stream. Thanks for watching.